In this video, we're going to continue our discussion of computing linear kinematics from rotating segments with some real numbers. And so this table presents some sample data of knee extension from the start position all the way to the final position. You'll notice here that I've changed the reference for the values where the start position of the leg is at 90 degrees, and we're taking the movement towards knee extension and final knee extension as 180 degrees. But time is going to be our independent variable here, so we've tracked the data, we've tracked the movement out to 1 second. So the leg, lower leg and foot the segment started with an angle of 90 degrees, and at 1 second it was captured at an angle of 159.37 degrees, referenced to a fully knee extended position of 180. So the first question we ask ourselves here is calculate the delta t. This is going to be critical in all of our in most of our calculations. So delta t in this case is 0.25 seconds. As we see, time is equally incremented by 0.25 seconds. And so the 0.25 seconds is essentially the line in between each of these rows of data. So the question here is, the instruction here is to calculate the angular kinematics of the lower leg and foot at t equals 0.5 seconds. So we want to be able to calculate the kinematics of what's going on at this point in the movement. So the first step is to calculate the angular the angular velocity, then calculate the angular acceleration. Of course, the second column here at each point is the angular position in degree units. And so if we go to our picture here, we see that in terms of the rotating variables, we have theta, omega, alpha, the three respective angular kinematic measures, and we will eventually move to calculating the linear kinematics of the foot. So what we want to do, this is where we want to target our interest, but if you notice here, although we have a delta t of 0.25 seconds, we only have one position, and that's 120.30 degrees. Now, of course, to calculate angular velocity, we need a final velocity subtract an initial a final position subtract an initial position. And so what we want to calculate is an angular velocity. It will, because we're dealing with a relatively wide time interval, it's still an average value, albeit over a very short period of time. But we want to calculate that angular velocity at t equals 0.5 seconds at this point. And so what we need to do is we need to take the position value in the period prior to the 0.5 and the position value in the period after the point of interest here. So the point afterwards will be the final. The position prior to will be the initial. So we want the position at 0.75 subtract the position at 0.25, as well as, and then divided by the respective time at 0.75, the respective time at 0.25. But because we have two lines, we now have two delta t's. So if we just work between two rows of data here, we would only have one delta t. But because we want to calculate, we want to use this value, the average will land us in the middle, which is where our point of interest is. We have two time intervals, so we have to divide it by 2 delta t. So I moved a little too quickly here. You might want to pause the video at this point, go through the calculation yourself, and when you restart the video, I'll step through the solution. So when we substitute the values from the chart, we have the position at 0.75, which we just read off the chart to be 147.83 degrees. We subtract that from the position at 0.25, which is 96.27. We already know delta t is 0.25, but because we have 3 rows we're working across, and hence 2 lines in between these 3 rows, we have 2 time intervals, so it's 2 times 0.25. When we work through the calculation, we'll arrive at a value of 103.12 degrees per second. Pause the video again. Now convert this value into radian units. So to perform this calculation and to get the degrees per second into radians per second, this is a process referred to as chain link conversion, where we have on the left-hand side the units we want, which is radians per second. On the right-hand side, we start with the units we have. So we have 103.12, that was our answer. So, and degrees per second. Now we just for a moment ignore the numerical value here and just isolate our view on the units, and we multiply the units we have by the relevant conversion of degrees and radians, ensuring that our entry of the units we have that we want to eliminate is going to be in the denominator. In terms of seconds, we want to end up with seconds. We have seconds. We can ignore that unit. We don't have to do anything with it. So we know that the conversion of radians to degrees is such that pi radians is equal to 180 degrees. When we perform that multiplication, we see that the degree units are eliminated, and what's left standing is 103.12 times pi radians divided by 180 seconds, and that will give us a final value of 1.80 radians per second for our angular velocity at this point in the movement, which is where our interest was. So we want to calculate the acceleration at that same point. So when we conduct our kinematic analysis, we want to isolate our view at the same point with all 3 variables. The problem here with acceleration, angular acceleration, is that we need 2 omega values. We need 2 angular velocity values. And so where do we get these? We use the same approach we did on the previous slide, but we use different rows to carry those out. So this is where we want to end up. This is our point of interest. Now, to get the acceleration that occurs at this point, we need an angular velocity averaged between this row, the 0.25 row, and the 0.5 row. That will give us our first angular velocity. And then we calculate a second angular velocity between the 0.5 and the 0.75 rows. That will give us 2 angular velocity values that will allow us to use the angular acceleration equation. So when we step through this, we find that the angular velocity across 0.25 and 0.25 rows is 120. Subtract 96.27. Remember, we're always doing a final subtract initial. And because we're only dealing with we're only calculating across 2 rows, we only have 1 delta t. We only have 1 line of separation, and that was established at 0.25. So that gives us a 96.12 degree per second value. For our second angular velocity value, we're working across the 0.75 and 0.5. So we have 147.83 in the 0.75 row. Subtract the 120.30 in this row right here. Remember, these are position values. Divided by the 0.25, so between 0.5 and 0.75, 2 rows, 1 line of separation, only 1 delta t. So we can therefore calculate the average angular acceleration value by substituting the values we just calculated, and so it's the we go through the 110.12, subtract the 96.12, divided by the delta t. Okay, so we only have one interval of time here, and that will land us here at the 0.5 spot. And then that will give us a value of 56 degrees per second squared. As we did with angular velocity, we have to convert our angular acceleration values into radians per second squared. And so we use the same chain link conversion method. So we know that what we want on the left-hand side are radians per second squared. What we have on the right-hand side is 56 degrees per second squared. So second squared, we're fine. We don't have to worry about that. We have to worry about the degree unit. So we multiply this unit, particularly as it relates to degrees, by the same conversion factor we did on the previous slide, where pi radians is equal to 180 degrees. So we make sure that the units we want to eliminate are on opposite sides of that fraction. So the degrees cancel. We carry out the mathematical step of multiplying 56 and pi divided by 180, and that gives us an angular acceleration at this point in the range of motion of 0.98 radians per second squared. So with those angular measures, now can we move to calculating the linear kinematics of the foot using the data that were provided? So we know that we have a few givens here. We have the angular velocity that we calculated in radians per second, 1.8 radians per second. The angular acceleration at 0.98 radians per second squared. And so we have the angular kinematics, theta, omega, alpha. What we want are the linear kinematics of the same part of the foot that was discussed in the previous video. So we want the tangential velocity, we want the tangential acceleration, and we want the centripetal acceleration that will direct us towards the resultant acceleration. So we start with the linear velocity of the foot. We have the only equation for the linear velocity of the foot, and that's r times the angular velocity, which is a given. The r was given previously, and so we have a length, lower leg and foot length of 0.42 meters. We multiply it by the 1.8 that we calculated for the angular velocity, and we arrive at a value of 0.76 meters per second, making note that the radian unit is unitless. So even though we go through the multiplication, the radian being unitless just drops out, and what's left standing is the meter per second for the foot. Now, moving on to the linear acceleration values for the foot, we start with the tangential acceleration of the foot because it has the same form as we had on the previous slide for the linear velocity, where we have the segment length as r and the angular acceleration at that point in the range of motion that we calculated earlier at 0.98 radians per second. So substituting the values, we substitute the length of 0.42 meters. We multiply that by the previously calculated value for angular acceleration at 0.98 radians per second squared. Once again, the radian unit is unitless, so performing the multiplication, the radian we just drops out, and we're left with a meter per second squared. The tangential acceleration of the foot at that point in the range of motion is 0.42 meters per second squared. Now, moving on to the second of the two linear acceleration values, we calculate the centripetal acceleration of the foot. So essentially, R will not change across the full range of motion, but we know that angular velocity will change. So the force that would tend to pull the foot towards the knee to counteract the centrifugal force that would pull the foot away from the lower leg is going to be a function to how fast it's moving, right? So how fast it's rotating in the angular velocity. Another good idea here to pause the video, go through the calculations yourself. And as you restart the video, what we see here is we have the same same segment length at 0.42 meters. We have the 1.8 that was calculated previously squared. And so once again, even if you square a radian, it's unitless, so it drops out. The second becomes a squared unit, and we're left with a meter per second squared. So since we want an acceleration, the units work out, so we're headed in the right direction. We perform the mathematical multiplication, and we have a centripetal acceleration of the foot of 1.36 meters per second squared. And to complete this calculation, we compute the vector sum of the centripetal and tangential accelerations of the foot using Pythagoras' theorem. And substituting the values, we have a resultant foot acceleration of 1.42 meters per second squared. And that resultant also has an angle with respect to the rotating segment defined by the arctangent of that foot, the arctangent of the ratio of the tangential vector magnitude divided by the centripetal vector magnitude, and that gives us a value of 16.8 degrees. Now, it's 16.8 degrees because my calculator was set on degree units. Your calculator may also be set on degree units, but you can also set it to radian units as well. So for solving a problem like this, when you get to the final answer, if you wish to keep it in radian units because your calculator was set to that, that's perfectly acceptable. If you wish to express it in degree units, perfectly acceptable as well. Sometimes, oftentimes actually, degree units are a little bit easier to envision than radian units. But when calculating linear kinematics from angular measures, we must always convert the angular measures into radian units if they're not given in radian units. So if we take a look at to sort of summarize the motion here, once again we have our angular kinematics, which we calculated first, our theta, omega, alpha. From that we calculate our linear kinematics, which is the arc length, tangential velocity, tangential acceleration, centripetal acceleration, and from these two we compute a resultant acceleration and an angle of that resultant vector with respect to the rotating segment. And if we take a look at the picture on the right hand side, we see at the very beginning the foot has a zero velocity because it's starting from a resting position. Going to jump all the way to point number 5 here, where the foot has a zero velocity, essentially where it stops moving at the terminal range. But it's going to achieve a peak velocity somewhere in the middle of that range of motion. So this gives us an overall picture of the kinematics of that leg as you go through a single cycle of knee extension. Now, in terms of drawing a kinematics graph, we're going to draw a graph where we place position, velocity, and acceleration all on the same graph, and we're going to use the graphical approach that we discussed with the linear kinematics video. So we're going to end this video here, and the next one we'll pick up by extending our calculations here to a graphical approach.